this video, I want to talk to you about my implementation of switch mode power supply step-down converters to regulate a 5-volt output rail and a 12-volt output rail from our 24-volt input voltage. To do this, we're going to use an integrated switch mode power supply controller with integrated high-side switch. By using this IC, we will have a design example to reference when creating our schematic, and that will reduce our part count when looking to solder this together on a PCB. In this video, we're going to talk a little bit about buck converter theory and how the currents are flowing through a buck converter to create a voltage regulated output. We're going to be stepping through the schematic design using the reference design mentioned earlier, and we're going to lay this schematic out on the PCB design. So when looking to design a switch mode power supply or linear regulator, we need to consider the power consumption or the power loss in the regulator or converter and what the overall efficiency of the system will be. For example, with a linear regulator stepping down 24 volts to 5 volts, you will have 5 volts on your output. Let's say you want 100 milliamps on that 5 volt rail. You want half of a watt on the output of your converter. However, to get that half of a watt on your output, you need to consume the voltage that you don't want with a linear regulator. So 24 volts minus 5 volts, 19 volts across your linear regulator, and the same 100 milliamps flowing through it. That results in approximately 2 watts of heat burned in your linear regulator just to get that half of a watt that you desire on the output. That's approximately 21% efficient. With a switch mode power supply, instead of continuously burning the power that you don't want, you are using an inductor and a capacitor to take energy from your input and create or transfer that to the output of your converter. Not directly, but through pulses. These pulses result in more output ripple than with a linear regulator. However, they are much more efficient. In this case, only the losses from the RDS(on) of your high-side switch and the forward voltage of your diode. In my design, I'm going to be using a Schottky diode, which results in a lower forward voltage than a traditional silicon diode. With this topology, we should be able to achieve approximately 94% efficiency with this converter. That said, there are some sensitive circuits on this board. I can't say how sensitive they are to ripple, but I would rather not design a second spin of this board simply because the output ripple on the 5-volt rail was too high. So, just to be on the safe side, we're going to leverage the efficiency of a buck converter to translate the voltage from 24 volts down to 6 volts, and then trim the remaining 1 volt with a linear regulator to achieve our final output voltage of 5 volts. This will ensure that there's very low ripple on our 5-volt rail, protecting our digital communications from corruption and ensuring that our system will operate more stably than if we had simply used a step-down buck converter. That's not to say that a buck converter would not have sufficient ripple performance to achieve our desired function, because we could design this switch mode power supply to do just that. However, like I said before, the goal here is to have a single spin of these boards and to achieve a function, to allow our plant light to operate day after day without resetting or losing your settings or corrupting the real-time clock. So I'm going to use this slightly overkill but effective approach to achieve a low noise, low ripple 5-volt power supply with high efficiency. In this case, approximately 80% efficiency is expected. Now for the 12-volt regulator, ripple performance isn't as important. This is simply driving a fan. So we're going to use the switch mode power supply to step directly from 24 volts down to 12 volts. This should be perfectly adequate for those fans with adequate ripple performance, and we'll be able to look a little bit more into the difference between the direct buck converter and the linear regulation after the buck regulation. With that, let's head over to the computer to dive a little bit deeper into buck converter theory and the schematic design as well as the layout of this design. Let's go. So now that we're at the computer, Let's take a look at this buck converter here. It follows the general principles of a buck switching converter. Right now the input voltage is set to 24 volts, the output voltage set to 6 volts, the output current set to 500 milliamps. The duty cycle is 23.5%, and the switching frequency is 100 kilohertz. Now, in general, with a step-down converter, the duty cycle is approximately equal to the ratio of your output and input voltage. Let's go ahead and calculate that here. 6 volts on the output, 24 volts on the input. That would come out to a duty cycle of approximately 25%. In this case, a duty cycle of 23.5% gives the intended function. Keep in mind, this is the step down from 24 volts to 6 volts that will end up being trimmed down to 5 volts with a linear regulator in our design. So, what you see here is a pulse source in LT Spice driving the MOSFET through a current limiting gate drive resistor. What this means is, since we are operating at a fixed frequency and fixed duty cycle, if we were to adjust this load resistor without adjusting the duty cycle, the voltage regulation would not exist. Our output voltage would vary based on the load current. This duty cycle is automatically adjusted by the switch mode controller IC to maintain a constant output voltage by monitoring the output voltage and the peak current through the inductor to intelligently set the duty cycle and vary the duty cycle with time to achieve low ripple constant voltage output. So, now let's dig into the heart of this analysis and look at how currents are flowing in this buck switch mode controller. Let's start by running the simulation. Here you see, at t equals 0, an output voltage of 0 volts, ramping up to our final desired set point of 6 volts. Let's zoom in on this output voltage. Like we mentioned before, this is not constant 6 volts, but instead has some ripple. This ripple aligns with the frequency of our controlling pulse source. I'm going to zoom in on that ripple. You can see the ripple voltage is periodic and in sync with the transitions of the pulse source. Awesome. Just as we would expect. Now, let's take a look at some of the inductor currents, or at some of the components that make up the inductor current. Let's start by plotting the inductor current. We're going to zoom in on a couple periods. Now, there are a few things that we can see about this waveform. First, we start with a current of 0 amps, ramping up linearly, or approximately linearly, to a peak current of 2.2 amps, and then decreasing approximately linearly back down to 0 amps. This means that we are operating in what is known as discontinuous mode, where there is not constantly current flowing through the inductor. In other words, there is a part of the period, or a part of the switching cycle, where there is no appreciable current flowing through the inductor. This ringing you see doesn't really count as current because there is no net current flow. This ringing is due to a fast slew rate, or this transistor is turning off very quickly, and there is no snubber network to consume that ripple, or that ringing. So, what happens is if we plot this pulse, my mistake, that was the current through the pulse source. If we plot the voltage present at the gate of this MOSFET, you can see when the MOSFET is off, so low, or turning on this PMOSFET, current flows, builds to the peak, and when the PMOSFET turns off, that is when the current through the inductor comes back down to 0. Now, instead of monitoring this voltage, let's go ahead and monitor the current flowing through this MOSFET. zooming in and ignoring the switching transients, you can see this current right here through the MOSFET is the same as the current through the inductor. So, looking at the circuit, knowing that we're looking at the inductor current, for this half or this part of the switching cycle, if the current is not coming through the MOSFET, then it must be coming through this diode because there's no other current path. Sure enough, adding this diode, or adding a plot of the current through this diode, clearly shows that when the current is not flowing through the MOSFET, the current is then flowing through the diode, just as we would expect. So, we have now determined that when the pulse source is turning on the gate of this MOSFET and current is allowed to flow through the channel of the MOSFET, the current builds in the inductor. Once this turns off, the current begins to ramp down in the inductor and comes through the diode. During different parts of this switching cycle, currents are either flowing into or out of the bulk capacitance. Let's take a look at a plot of the capacitance, removing the different components that make up the inductor current. Notice the difference between the inductor current and the capacitor current is that when the inductor current has reached 0 amps, the current is flowing out of the capacitor into the load. To demonstrate this fact, I'll zoom in on a couple switching cycles, and instead of plotting only the capacitor current, I will plot the capacitor current plus the load current. Notice it seems as though the capacitor current plot has disappeared, or rather the inductor current plot has disappeared behind the capacitor current plot. This demonstrates that the difference between the capacitor current and the inductor current is the relative constant offset of the load current. I say relatively constant because the output voltage is varying slightly within each switching cycle. Since the load is set to a constant resistance, that means the current is also varying very slightly. It's a negligible difference for this example. So, looking at a few switching cycles, zooming in further, there are 4 main regions of this waveform repeated once every period. There is the part of the waveform here, where the capacitor is sourcing 100% of the load current. There is the region while the inductor current is spooling up to 500 milliamps, or our load current, where the capacitor and the inductor are sharing the load, both contributing some of the current into our load. Then, there's the part of the waveform when the inductor current has exceeded 500 milliamps, and the inductor is both sourcing the current into the load as well as charging the capacitor for the next part of the switching cycle where the capacitor is discharging again. Leading us to the third part of this waveform, where the inductor current has fallen below our load current, in this case 500 milliamps, and we see that the capacitor current drops below 0 amps, beginning to discharge once again. Leading us back to the first part of the switching cycle, where the capacitor is sourcing 100% of the load current. This repeats cycle after cycle. One key point here is that the charge moving in and out of the capacitor each switching cycle must be constant. If the charge flowing in and out of the capacitor is not constant, that would result in varying of the output voltage, V output, over time. Since our output voltage, as we showed before, is relatively constant with only a small voltage ripple, there is no appreciable charge accumulating in the capacitor. To demonstrate this point, instead of plotting the capacitor current, I'm going to plot the power coming in and out of the capacitor such that we can plot the net charge over a certain window of time. To do this, I will multiply the current flowing in the capacitor times the output, the net where it is connected. Now, to demonstrate that the charge flowing in and out of the capacitor over a discrete number of switching cycles is approximately zero, I will highlight this point by first showing you my best approximation of the current flowing through a finite number of switching cycles, the charge flowing through one switching cycle when the capacitor is discharging, and then the charge flowing out of the capacitor when it's discharging. First, I will attempt to zoom in on a discrete number of switching cycles. There we go. And I will plot the integral, in this case 534 nanojoules, to demonstrate the difference between that and the part of the switching cycle when the capacitor is charging. I will grab from the peak down to where the discharge is 0 watts for this capacitor and plot that. Here we see 3.7 microjoules, or a few orders of magnitude larger power or charge than we were seeing before. Let me zoom out again. And I will grab only the part of this waveform where the capacitor is discharging, or when the power is negative. And I will plot the integral here. Oh, looking at my selection, it grabbed some area where it was still positive. There we go. That selection is much better. And now we see, again, microjoules instead of nanojoules. In this case, I'm making my selections manually, so they're not perfect, but this demonstrates the point that there is significant charge being stored in and taken out of the capacitor, the bulk capacitor on the output. However, there is no net charge or discharge in that capacitor or from that capacitor. That is key to the way that a switching regulator operates. Without this bulk capacitance, it is impossible to have a switching regulator. The more bulk capacitance you have, the longer it will take your output to rise to its final value, but the lower your ripple voltage will be. With this in mind, I've demonstrated when during the switching cycle current is flowing through the MOSFET, when during the switching cycle current is flowing through the diode, when during the switching cycle there's current flowing into and out of the bulk capacitance, and this all achieves a relatively constant voltage across and current through the load. Well, now that we've talked a little bit about how the currents are flowing in these buck converters and the theory behind a switch mode power supply, let's go ahead and implement a switch mode power supply in a schematic and on a PCB in KiCad. Today we were able to talk about the differences between a switch mode power supply and a linear regulator. We were also able to discuss in more detail how a buck step-down switch mode power supply works. Unfortunately, to cover modifying and implementing a datasheet reference design in enough detail to be useful, I needed to split that off into its own video. I hope that you learned something great today, and I hope to see you again soon. Bye!